In this lecture, we are going to talk about integration by parts. This is a way of computing integrals of product of two integrable functions. We will derive this integration by parts as a consequence of the fundamental theorem of calculus part 2, which I have kept here in this lecture for easy reference. So just recall what does fundamental theorem of calculus part 2 told us. It told us that if f is a differentiable function and f prime, which is the derivative of f, is an integrable function and both are happening in the closed interval ab, then we can easily compute the integral of f prime x dx, where the integral goes from a to b. And this will always turn out to be equal to fb minus fa. Now what does integration by parts say? We have written down this in a form of a proposition. So suppose f and g are two functions, two real valued functions on the closed interval ab, and they satisfy the following conditions. So f is a differentiable function on closed interval ab, and f prime is an integrable function on the closed interval ab. So this puts us in the situation of FTC part 2, but we are not going to really use it on the function f. We will see how we will use it in the proof. Let's go forward. G is an integrable function on the closed interval ab with an antiderivative big G on ab. So that means that there exists a function big G which is differentiable such that G prime is equal to small g on the interval ab. Then if we try to compute the integral of fx gx in the closed interval ab, what we are going to get is fb times big gb minus small fa times big ga minus integral of the function f prime x gx big gx on the interval closed interval ab. So let me try to prove this for you. The proof is not difficult, I must admit, and so this is why it is important to know the proof of this kind of things. So here let us define a function h from a b to r given by hx is small fx times big gx. So what can we say about hx? So we know that what are we given with? We know that f is differentiable on ab, and we also know that big G is an antiderivative. So by definition G is also differentiable on the closed interval ab. So we know that product of two differentiable functions is the differentiable function. So we derive that big hx is differentiable on the closed interval ab. So let us try to compute the derivative of h with respect to x. So we see that this is equal to fx times small gx. Remember that small gx was the derivative of big gx plus f prime x times gx. This is simply the product rule of for differentiation. Okay, fair enough. Now we know that f is differentiable on ab. That means f has to be continuous on ab as well. And we know that continuous functions are integrable. So f is integrable on ab. Right? Similarly, by the same argument, we see that g is integrable on ab. So now what do we have? So what did we know about small g? So small g was integrable, and of course, so now let's see. So we know that f is integrable, we know that small g is integrable, we have seen that small f prime is integrable. This was one of our conditions. So small f prime is integrable, and we have just derived that big G is also integrable. So by algebra of Riemann integrable functions, or by algebraic properties, we see that product of integrable functions is integrable. So fx gx, small fx times small gx, this is integrable. Similarly, this product is also integrable, and we know that sum of two integrable functions is integrable. Please do not write on any formal expositions or exams like this, but this is just for a informal understanding for you. So what we have is that the whole function h prime x is integrable. So what we have shown that h prime x is integrable on the closed interval ab. So let me now wipe this off. I do not want to have this uh, on my notes. So h prime x is integrable. We also know that small hx is differentiable. So here comes fundamental theorem of calculus part 2. So what do we know about it? We know that integral on the closed interval ab of the function h prime x dx is equal to hb minus ha. Don't forget what was the function h yet. hx was defined as small fx times big gx. Okay, so let me write down using the product formula. This is going to be, as we have mentioned before, so this is fx times gx dx equal, okay, so plus integral ab f prime x times big gx dx equal to hb. What is hb? hb is fb times gb minus fa times big GA. So if you compare this formula that we have derived with the statement that we had in the beginning, you will see that this was the exact statement that we were looking for. So this completes the proof of the proposition related to integral by parts. We will conclude this video with a small example. So let me try to work out an example for you. So here we are trying to compute the definite integral on the closed interval 0 1 for the function x times 1 minus x dx. Okay, so let us see. So here let us denote by small fx the function x, gx the function 1 minus x. So remember, we wanted f to be differentiable on ab, f prime integrable on ab, g should be integrable on ab, and there should exist g, a differentiable function such that g prime should be equal to g on the closed interval ab. I leave it to you to check these details, that f is differentiable clearly, f prime is integrable, f prime is after all a constant function, g is integrable. This will be a good exercise for you to check, and and I will just write down what could be a potential value of G. You can see that if you take big Gx to be equal to minus 2 by 3, 1 minus x to the power 3 by 2, then it works for us. So clearly this big Gx is also an integrable function. So we have written it as a product of two functions satisfying the hypothesis of integration by parts. So we can now apply integration by parts. So let me try to do it for you. So this is going to be, we have the formula here. So f of 1 g of 1 minus f of 0 g of 0 minus integral of 0 to 1 f prime x. F prime x is just 1. So big gx is this function. So 2 by 3 minus 2 by 3, 1 minus x to the power 3 by 2. Now what is f of let's say big G of 1? We see that big G of 1 is equal to 0. And what is small f of 0? This is also equal to 0. So that means that this product is equal to 0. Also this product is equal to 0. What does that give us? This leaves us with the quantity, that this integral that we started with, 0 1 x times 1 minus x dx is equal to integral, okay, I can take 2 by 3 out, 0 by 1, 1 minus x to the power 3 by 2 dx. So if I now call this function small hx, and this function is given by 1 minus x to the power 3 by 2, and I take a function h tilde x, so this is on the interval 0 1, and h tilde x, this is also on the interval 0 1. How do I define it? Minus 2 by 5 and 1 minus x to the power 5 by 2. You can easily see that h prime x is equal to hx for all x in the closed interval 0 1, and that all the conditions in the hypothesis of fundamental theorem of calculus 2 are satisfied. On this note, let me use fundamental theorem of calculus here, part 2, and what do we now know about it? This will be h tilde, so 2 by 3 times h tilde of 1 minus h tilde of 0. Fair enough. So what is h tilde of 1? H tilde of 1 is equal to 0, that you can easily see. And what is h tilde of 0? H tilde of 1, this is equal to 0. And what is h tilde of 1? This h tilde of 1 is 0, and h tilde of 0 is going to be minus 2 by 5. So this is going to be 2 by 3 times minus of minus 2 by 5, and this is going to be 4 by 15. So this is how we are going to use our result on integration by parts. One concluding remark. So we have seen that if f and g are integrable functions, are integrable, then if g is integrable, this was one of the statements of our algebraic properties, and we have we had said that integral a b f g is not necessarily equal to integral f times integral g. This you can see from here, but also here the assumptions were much bigger. We see that even though we are considering g to be, and this small g to be, an integrable function, So this if is a very small comes from a very small class of function. So this follows from the argument here. So if this is the class of all integrable functions, and here we know that any continuous function, so continuous function, any continuous functions is integrable. So if this is the set of all continuous functions, the class of all differentiable functions, let me put this in a different color, this is a much smaller thing than this. So all I wanted to tell you was that we have not yet dealt with the case when f and g are both integrable functions. So here we have treated the cases when f and g are integrable, but f comes from a very small subclass of functions. So in the next video we will talk about integration by substitution, work out one or two examples, and we will go forward. For now, thank you.